Okay, in today's lecture, we're going to cover the section 2.2 material on the inverse of a matrix. So in the last section, 2.1, we had introduced some matrix operations, and one of the operations that we introduced was matrix multiplication. And what we're going to try to introduce in this section is the concept of something that would be equivalent to matrix division. And really, instead of division, we think about multiplication by an inverse. So to introduce the idea of an inverse matrix, let's consider what we would think of as division or multiplication by an inverse for the real number system. So let's consider the set of all real numbers, R. Now, for the set of real numbers, we have what's called a multiplicative identity, which would be the number 1. Now, why is this called the multiplicative identity? Well, for the real number system, for any real number A, if we take A times 1, or 1 times A, we get back the value A. So the number 1 is called the multiplicative identity because if we multiply any real number by 1, we get back the same real number. Now, we can introduce the idea of a multiplicative inverse once we have that multiplicative identity element. So in particular, for any non-zero real number, let's call it A, we have something called a multiplicative inverse, which is usually denoted as A inverse, or 1 over A. And this multiplicative inverse satisfies the following equations. A times its inverse, or A inverse times A, is equal to 1. That is, I have some number which I'm able to multiply a given number by, which will take me back to the multiplicative identity element. So for instance, the inverse of, say, 4 would be 1/4. It's the number that I multiply by to take me back to that multiplicative identity, which in this case is 1. So what we're going to be considering in this section is whether or not matrix multiplication, so if we consider the set of all matrices that have real entries or real elements, does matrix multiplication have a multiplicative identity? Is there some matrix that acts like the number 1, where if I multiply any matrix by that matrix, I get back the same thing? Or does a given matrix have a multiplicative inverse? Is there some matrix that I could multiply a given matrix by that would take me back to that identity for matrix multiplication? So to answer the first of those questions, is there a multiplicative identity? Yes, there is. So let's define it. So here we define what's called the identity matrix as the diagonal matrix that has all of its diagonal entries equal to 1. And when we talk about matrix multiplication, well, for given matrices, we have to be a little careful about what the dimension of a matrix is so that the product would be defined. So when we are referring to specifically the n by n identity matrix, that would be the matrix which we would denote as I sub n. So the subscript here, n, denotes the number of rows and columns. Or sometimes we simply use I if the dimension is clear from the context. So the 1 by 1 identity matrix, I1, would be the 1 by 1 matrix whose only entry, which would be a diagonal entry, is 1. The 2 by 2 identity matrix, I2, would be the 2 by 2 matrix, which is a diagonal matrix with 1s on the diagonal and 0s everywhere else. Similarly, the 3 by 3 identity matrix would be the 3 by 3 diagonal matrix, which has 1s on the diagonal and 0s everywhere else. So we've already referred to this identity matrix a little bit in our last chapter when we were looking at the matrix of a linear transformation. Remember, the columns of these identity matrices we were calling basis vectors, maybe E1 and E2, or E1, E2, and E3 were these columns of what we were calling the identity matrix. Now we have a more formal definition of this identity matrix. So more generally, if we want to define an identity matrix of general dimension, well, it would be the matrix I, which is a diagonal matrix with 1s on this main diagonal and 0s for all other entries. If we need to be a little specific, we can use the subscript notation to denote what the size of our identity matrix is. Now, this identity matrix is the multiplicative identity for matrix multiplication. So what we mean by that is if A is any arbitrary m by n matrix, so m rows by n columns, then the identity matrix satisfies the following. A times the n by n identity matrix is equal to the m by m identity matrix times A, and they're both equal to A. So that is, for any matrix A, it doesn't matter what order I take the product of A with the identity matrix, as long as the dimensions agree. I'm guaranteed to get back the same matrix A. So this identity matrix I acts like the real number 1 would for multiplication in the real number system. Any matrix times that identity matrix gives us back the matrix A. Now, we could ask the question, well, is there a multiplicative inverse? So if I have a matrix A, is there some matrix I could multiply it by such that the product would give me back the identity matrix? And the answer is no, not every matrix has a multiplicative inverse. So some terminology we're going to introduce here is the following. In this course, we're going to be working almost exclusively with square matrices when we talk about invertibility. So here, a square matrix A is said to be invertible if there exists some matrix, let's call it B, such that A times B is equal to B times A, and both products give the identity matrix. And in this case, if such a matrix exists, this matrix B is called the inverse of A and is denoted as A inverse. So what we have here is that the product of A with its inverse is equal to the identity matrix, provided that this matrix is invertible. Turns out that not every matrix will be invertible, just like every real number is not invertible. For instance, 0 is not invertible in the real number system. There's no number that I can multiply by 0 that would give me 1, the multiplicative identity. So we'll see in this course that not all matrices are invertible. There are some matrices where no matter what you multiply by, you cannot get back to the identity matrix. So any matrix which is not invertible is called a singular matrix, and invertible matrices are sometimes referred to as non-singular matrices. So a matrix is said to be either invertible or non-singular, or if it does not have an inverse, we say it is not invertible or it is a singular matrix. Okay, So now that we've introduced these concepts of a multiplicative identity for matrix multiplication and the concept of an inverse matrix, let's look at some properties that inverse matrices might have. So in this next theorem, we're going to consider some properties of inverse matrices. So property number one is if A is an invertible matrix, then A inverse is also invertible. And the inverse of the inverse is the original matrix. So if I'm able to find an inverse of a given matrix, that means that the product of them in either order gives me back the identity. So it follows immediately that, well, if we have an inverse matrix, it must also be invertible, because if I were to multiply it by the original matrix, I'm guaranteed to get back the identity. Now, property number two says if A and B are invertible square matrices, then the product A times B is also invertible, and the inverse of the product A times B is equal to the product of B inverse times A inverse. So notice that the order of those factors changes here. A times B inverse is given by B inverse times A inverse. So recall here the order of that multiplication is important. And then our third property is if A is an invertible matrix, then so is A transpose, and the inverse of A transpose is equal to the transpose of A inverse. So if we have an invertible matrix and I need to find the inverse of a transpose, I can just take the inverse matrix of A and then take its transpose. All right. So let's consider some examples where we'll start to work with inverse matrices. So one a nice type of problem that we'll consider here, it's something that you might want to do in your work throughout this course. Let's say that you're trying to find an inverse matrix and you think you have found one. Can you verify that what you found is actually the inverse of the matrix you were given? So in this first example, we're given two matrices, A and B, which are both 2 by 2, and we are asked to verify that A and B are inverses of each other. So to verify the two matrices are inverses, we need to take their products and make sure that we get back the identity matrix. So let's start here by considering A times B. So here A is 2, 5, -3, -7, and B was -7, -5, 3, 2. So for the product of two 2 by 2 matrices, we get back a 2 by 2 matrix. And to get the entry in the first row, first column, we're going to take the first row and first column of these factors and look at their dot product. So for this one, we would have -14 plus 15, which leaves us a +1. For my first row, second column, I'm going to take the dot product of the first row and second column of these factors. So here I have -10 plus 10, which is 0. Then moving to my second row, first column, taking the dot product of the second row and first column, I have +21 minus 21 is 0. And then the second row, second column, taking our dot product of the second row and second column vectors, we have +15 minus 14 is 1. So for A times B, we get back this diagonal matrix with 1s on the diagonal and 0s elsewhere, which is exactly the 2 by 2 identity matrix. So A times B is equal to I. Now, does that mean that they're inverses? Well, there's one other thing that we need to check. We found that A times B is equal to the identity, but recall matrix multiplication is not commutative in general. So we also need to consider B times A. What if we were to reverse the order of this product? So here B is the matrix -7, -5, 3, 2. And then we're multiplying by the matrix A, which was 2, 5, -3, -7. So we get back a 2 by 2 matrix, and for the entry in our first row, first column of the product, we take the dot product of this first row and first column vector. So here we have -14 plus 15 is 1. For the first row, second column, we have -35 plus 35, which is 0. For our second row, first column, we have a 6 minus 6 is 0. And for our second row, second column, we have 15 minus 14, which is 1. So if we reverse the order of the product there, we still get back the identity matrix I. So here, since A times B is the same as B times A, and both products give the identity matrix, it follows that A and B are inverses of each other. Okay, so this type of example or this type of problem is something that you'll often want to do in this course. Let's say that you think you have an inverse for a matrix. Can you verify that it is an inverse? And recall that to check whether two matrices are inverses, we would need to look at the products of those two matrices in either order and make sure that we get back the identity matrix. Now, the question becomes, well, how do we find the inverse of a given matrix? Or more importantly, if we have a matrix, can we determine whether it is invertible? Does an inverse even exist? Now, for square matrices, there is a scalar or a number associated with each square matrix that tells us whether it is singular or non-singular. That is, whether it has an inverse or not. And in this section, we're going to introduce that number specifically for 2 by 2 matrices, and then consider this in much more detail in Chapter 3. But in this section, we will introduce what's called the determinant of a 2 by 2 matrix. So let's say that we have a square matrix A, which is 2 by 2. Its entries are A, B, C, D. The determinant of that matrix is the scalar, or the number, 1 by 1 matrix, which is denoted as det of A, so determinant of A, or sometimes it's denoted by writing the matrix A, B, C, D with vertical bars around it instead of brackets or parentheses. So it sort of looks like we're putting an absolute value around the entire matrix. That's another notation for the determinant. And for 2 by 2 matrices, the determinant is defined as the product of the diagonal entries A times D minus the product of the off-diagonal entries B times C. So here, the determinant of a 2 by 2, again, is the product of the diagonals AD minus the product of the off-diagonals B times C. And it turns out that this determinant of the matrix A will determine or tell us whether that matrix is singular or non-singular. So how does this work? Well, in particular, a 2 by 2 matrix A is non-singular, that is, it has an inverse, if and only if the determinant of that matrix is non-zero. So we'll see that result more clearly in the next chapter, why this determinant guarantees that an inverse exists. So let's say that we have a 2 by 2 matrix and we calculate its determinant and we find that it's non-zero. Well, that means that the given matrix is non-singular. It has an inverse. So how do we find the inverse? So here, the inverse of a 2 by 2 matrix actually has a pretty simple formula, which is given in the following theorem. This is a formula for the inverse of a 2 by 2 matrix. And so here's what it says. If A is the 2 by 2 matrix whose entries are A, B, C, D, then the inverse of that matrix, denoted as A inverse, is found by the following. So we have a constant 1 over the determinant of A. So recall, in order for A to be non-singular, the determinant has to be 0, so that we don't have division by 0 here. So we take 1 over whatever the determinant is times the 2 by 2 matrix that we get by performing some operations on the matrix A. So what do we do with the matrix A? Well, we take its diagonal entries, A and D, and we switch them. They become D and A. So we interchange the diagonal entries, A and D, and the off-diagonal entries, B and C, are made negative, or we take the opposite sign of whatever the off-diagonal entries are. If they're negative, they become positive. If they're positive, they become negative. For the 2 by 2 matrix, as long as this determinant is non-zero, that means the matrix is non-singular, it has an inverse, and this theorem gives us a formula for calculating the inverse of that matrix. So let's consider finding the inverse of some 2 by 2 matrices. So in this next example, we are asked to determine first whether a given matrix is non-singular, and if it is, we want to find its inverse. So in part A, we have the following 2 by 2 matrix, and to determine whether it is non-singular, we look at the determinant of A, which is found by taking the product of the diagonal entries of A, that is 3 and 4. So for a product, we have 12. And we subtract the product of the off-diagonals, which were 5 and negative 2. So we're subtracting a negative 10, or adding 10. And we have a determinant of 22, which is certainly non-zero. So as long as this determinant is non-zero, that means that A is non-singular or invertible. And to find the inverse, we can use the formula given by our theorem. So A inverse is given by 1 over the determinant, which we found to be 22, times the 2 by 2 matrix that we get by taking the diagonal entries of A, those were 3 and 4, and switching them. So we have 4 and 3. And then our off-diagonal entries, which were 5 and negative 2, we change the sign of. So these become a negative 5 and positive 2. And now simplifying, well, we're taking a scalar multiple, 1 over 22, of our matrix. So we know we just apply that scalar to each entry of our matrix. So we have 4 over 22, negative 5 over 22, 2 over 22, and 3 over 22 for the inverse matrix. Or if you want to simplify the entries in the first column of this matrix, you could say 12 over 11 or 2 over 11 or 1 over 11 for the entries in that first column. So let's look at another one. In part B, we have the matrix B, 2, 4, 3, 6. So we want to know, first off, is it non-singular? Does an inverse exist? So here, looking at the determinant of B, well, the product of the diagonal entries would be 12. And then we're subtracting the product of the off-diagonal entries, which is also 12. So we're left with a determinant of 0, which means that our matrix B is singular, and so B inverse does not exist. So this matrix B, or the determinant of a matrix, is telling us whether or not it is invertible. All right. And we'll see as we keep moving through the course why exactly that determinant tells us whether a matrix is non-singular. All right. Now, we're going to start talking about how we can use an inverse matrix to solve a system or systems of linear equations. So let's consider the following. Let's suppose that we have a system of n linear equations in n variables. So we have as many equations as variables. So here that system would have the following form. Our first equation in the variables x1, x2 up through xn would have coefficients a11, a12 up through a1n. And the linear combination of those variables x1 through xn is equal to some constant b1. Then our second linear equation would be of the form a21 x1 plus a22 x2 up through a2n xn is equal to some other constant b2. And then we have up through n equations. So we have some coefficient a n1 times x1 plus a n2 x2 up through a nn xn is equal to bn. All right. Now this system can be expressed in matrix form much more concisely as a single equation of the form a times x is equal to b, where a is the matrix whose ijth entry is a sub ij. So the entries along the first row of that matrix would be a11, a12 up through a1n. The second row would be the entries a21, a22 up through a2n, and so on. So we have here an n by n coefficient matrix. So its entries are just the coefficients of x1 through xn for this system of equations. And x, which is a vector of unknown variables, xi, would be an n by 1 column vector of these unknown variables, x1, x2, up through xn. And b is the vector whose entries are b sub I, these constants on the right-hand side of the equation, b1, b2, up through bn. So using the definition of matrix multiplication, when we've already seen this in our chapter 1 material, we can express this system of linear equations as a matrix equation, a times x equals to b. And our goal in solving a linear system is to find this vector of unknowns. What are the variables, x1, x2, x3, up through xn, that would satisfy this equation? So let's think about how to find this. If we were trying to solve a scalar equation, let's say we had a little scratch work up here, something of the form a times x is equal to b, where a, x, and b are all just scalars instead of matrices or vectors. To solve for x, well, we would take b divided by a. Or equivalently, we could think about multiplying both sides by a inverse. A inverse times b would be our solution for x, as long as a had an inverse, that is, as long as a was some non-zero number. So we have a similar concept for this matrix equation. For a times x equals to b, if we want to solve for x, well, we would want to sort of divide both sides by the matrix A. Now, here we don't really have anything called matrix division, but equivalently, we have something called multiplication by the inverse. So if I were to multiply, rewrite this a little bit cleaner to the side. So if I have the equation a times x is equal to b, and I multiply both sides of this equation on the left-hand side by a inverse, then on this left-hand side, my a inverse times a is the identity matrix. It acts as the number 1. So I would have the identity matrix times x, which would give me x, is equal to a inverse times b, as long as a inverse exists. So that discussion is summarized in the following theorem. If A is an invertible in by n matrix, so if it has an inverse, then for each b, for each vector b in Rn, the equation ax is equal to b has a unique solution given by x is equal to a inverse times b. So if the coefficient matrix for our system is invertible, then the solution of our system is found as x is equal to a inverse times b. So using that information, let's look at an example of solving a system of linear equations by using an inverse matrix. So in this next example, we have a system of two equations in two variables, x and y, and we're told to solve this using the inverse of the coefficient matrix. So let's first write this system in matrix form. So here I'll say in matrix form, our system can be written as follows. So we would have a coefficient matrix where the coefficients in our first equation are 4 and 3, and the coefficients for x and y in our second equation are 3 and 2. So this is my coefficient matrix, what we've been calling A, times some vector of variables. Now here, my variables were x and y. We could have maybe also called them x1 and x2 if we prefer. So this vector of variables is what we call the vector x. And this is equal to a vector of constants on the right-hand side of our equation. In this case, 5 and negative 1, which is what we've been calling this vector b. So in order to solve for x, well, I need to know if this matrix is invertible. That is the coefficient matrix A. Now, how do we tell whether a 2 by 2 matrix is invertible? Well, we could look at its determinant. So here, the determinant of A would be the product of the diagonals. So 4 times 2 is 8, minus the product of the off diagonals. So 3 times 3 here gives us 9. And our determinant is -1, which is certainly non-zero. So if we have a non-zero determinant, that means that A is non-singular, and we can calculate its inverse using the formula that we had from our previous theorem. So here, recall the formula for A inverse. We start by taking 1 over our determinant, so 1 divided by -1, or just -1, times the 2 by 2 matrix that we get by interchanging the diagonal entries of A. So we have 2 and 4 for our diagonal entries. And the off diagonals, we change the sign of. So our off diagonals are now both -3. So distributing our scalar out in front, which was -1, through to this matrix, A inverse is -2, 3, 3, -4. Now, once we have A inverse, we're able to solve our system. Recall that the solution of this system is given by x is equal to A inverse times B. So let's look at that down here. We have the unknown vector x is given by A inverse times the vector B. So here we just found A inverse was -2, 3, 3, -4. We're multiplying that by our vector B, which was 5, -1. So here we have the product of a 2 by 2 matrix with a 2 by 1 vector. So that will give us back a 2 by 1 vector, where my first row, first column is found by taking the first row and first column, which is the only column of B in this case, and taking their dot product. So here we have -10 minus 3, so -13. And for our second row, first column, we take the dot product of the second row and first column of A inverse and B. So here we would have 15 plus 4 is 19. So recall this vector is the vector whose entries are x and y. So the solution to this system would be the point x equals -13, y equals 19. Now, we could have also found the solution of the system using an augmented matrix and using row reduction. And it looks like this method that we used here of calculating the inverse was a little more tedious. So we might ask the question, well, why would we use the inverse here? And well, one reason is that the problem tells us we have to use the inverse of the matrix in order to solve this. But another reason that we might want to use the inverse is, let's say that we had this exact same system of equations, but I changed my constants on the right-hand side. Let's say instead of 5 and -1, I had 7 and -20. So if I were to use a augmented matrix to solve my system initially, whenever I make this change of those constants on the right-hand side, I would have to calculate or find a new augmented matrix and go through the row reduction all over again in order to solve. And then let's say I made another change of those constants, and then I would have to do it a third time. So any time that I change the constants on the right-hand side, I would have to go through a different row reduction. But if we make use of the inverse matrix, it doesn't matter what the constants on the right-hand side are. I have some vector of those constants b, so I can find out whatever they are depending on what constants I decide to change them to. And once I calculate A inverse out in front, well, I just take that same matrix that I found for A inverse and just multiply by the new vector of constants, and I've got my solution right away. So as long as the coefficient matrix for our system does not change, that A inverse matrix can be used to solve any system that has those same coefficients, even if we change the constants on the right-hand side of our equation. So that's one benefit to working with an inverse matrix in solving a linear system instead of using that row reduction algorithm. So another way that we can determine whether matrices are invertible is by performing row reduction on a matrix. In our section, we were talking about something called the determinant for 2x2 matrices, and that told us whether our matrix was invertible. But what if we had a matrix that was not 2x2, say a 3x3 or something else, and we want to know whether that matrix is invertible? So how can we check that? Well, another test for whether a matrix is invertible is the following theorem. So if we have a square matrix A, some n by n matrix, that matrix is invertible if and only if the matrix A is row equivalent to the n by n identity matrix. So that is, if it's possible to transform our matrix A into the identity matrix through performing row reduction, then that matrix is invertible. And in this case, any sequence of elementary row operations which would transform the matrix A into the identity matrix would also transform the identity matrix into A inverse. So this theorem gives us a criterion to see whether a given matrix is invertible. That is, if we can row reduce it to the identity matrix. And it also gives us a way to calculate an inverse matrix. So say if we have something other than a 2x2 and we can't apply that formula that we had in our earlier theorem, then how do we calculate our inverse? So what this theorem says, the second part, is if we take the sequence of row operations which we performed on A in order to transform it into the identity matrix, and we perform those same operations on the identity matrix itself, our result will be A inverse. So using that information, we can state the following. A convenient way to compute the inverse of some matrix A is to merge the matrices A and the identity matrix into a single augmented matrix, so something of the form AI, where the matrix that we're given A and the identity matrix we might separate by a vertical bar, or I believe in your textbook they omit that vertical bar in the middle. As we saw with augmented matrices in chapter 1, it's beneficial to write that vertical bar to help you distinguish which matrix is A and which one is I. That's notationally a little easier. Now, once we express that augmented matrix A and I together, then we would apply these elementary row operations in order to transform this augmented matrix to the form I times A inverse. So I'm trying to take the matrix A, which is the left-hand side of my augmented matrix, and perform row operations to transform it into the identity matrix. And our theorem that we just looked at said, well, that same series of operations, so if I'm performing the same operations on the identity matrix I, which is the right-hand side of this augmented matrix, it will transform that matrix into A inverse. So this is a convenient way that we will use to calculate the inverse of certain matrices. So let's look at an example of this and see that this method agrees with the theorem that we had earlier. So if we have a matrix A, which is 2 by 2, let's say it's 2, 5, 1, 3. In part A, we're supposed to show that that matrix A is non-singular and find its inverse using the formula for the inverse of a 2 by 2 matrix that we saw previously. So first part is to show that this matrix is non-singular. Now, in order to show that the matrix is non-singular, well, we could look at the determinant of this matrix A, which would be 2 times 3, or 6, for the product of the diagonals, minus 5 times 1 is 5 for the product of the off diagonals. So we're left with a determinant of 1, which is certainly non-zero, which means that A is non-singular. And to find its inverse, we would take 1 over the determinant, which was itself 1, so we just have a constant of 1 out in front of our matrix, times the 2 by 2 matrix we get by switching the diagonals of A, so we now have 3 and 2, and the off diagonals are made negative, so we have, instead of 5 and 1, negative 5 and negative 1. Now in this case, our 1 over determinant out in front of the matrix is just reducing to 1. So for A inverse, we're left with 3, negative 5, negative 1, and 2. And recall here, I'll stress again, we could always check that this would indeed be the inverse of A if we were to take this matrix and multiply by the matrix we were given A. We'll see that we get back the identity, so we know that our answer is correct here. We can always check that. Now in part B, we are told to find the inverse of the matrix A by using an augmented matrix and performing row reduction. So we want to illustrate another way that we could find the inverse by making use of this augmented matrix approach. So recall, the general idea for that method is to take an augmented matrix of the form A and I. So I'm going to take the matrix I was given, which was 2, 5, 1, 3, and then augment that with the identity matrix. So in this case, we're looking at a 2 by 2 identity, since the given matrix was 2 by 2. So that would be the matrix 1, 0, 0, 1. So here I have my matrix A and my matrix I expressed together as a single augmented matrix. And my goal is to perform row reduction in order to transform this to something of the form I, A inverse. So I want to transform the matrix on the left-hand side of this augmented matrix into the identity. All right. So there's several ways I could go about doing it here. I think for myself, my personal preference would be to take row 1 and subtract row 2 from it. And the reason I'm doing that is that now my leading entry in the first row will be 1. My 2 minus 1 gives me 1. 5 minus 3 is 2. And my second row I'm going to leave alone for right now, 1 and 3. And whatever operation I performed on this matrix A, which is the left-hand side of the augmented matrix, I want to perform that same operation on the identity matrix, which was on the right-hand side. So taking row 1 minus row 2 from the identity matrix, I have 1 minus 0 and 0 minus 1. So I have 1, negative 1 if I perform that same operation on this 2 by 2 identity matrix. And my second row I was leaving alone. I'm still going to have 0 and 1. So let's keep moving. Now I have the 1 in the lead position that I wanted. I need to eliminate the 1 that appears below that. So I could accomplish that by taking row 2 and subtracting row 1 from it. So row 2 subtracting row 1 gives me 0 and 1. And my first row I'm going to leave alone for right now. I've got 1, 2. Now if I perform those same operations on the right-hand side of this augmented matrix, well, I was leaving my first row alone. So I'm still going to have 1 and negative 1. But taking row 2 and subtracting row 1 from it, I would have 0 minus 1 is negative 1, and 1 minus a negative 1 would give me 2. So for my matrix on this left-hand side, I now have 1 for my lead coefficient, 0 below it. In the second row, I have 1 for my lead coefficient, but I need to kill off the 2 that appears above it in order to get the identity matrix there. So in my last step, I'm going to take row 1 and subtract 2 times row 2. So on the left-hand side, I have the matrix 1, 0, 0, 1, which is the 2 by 2 identity. And let's see what we have on this right-hand side if we perform those same operations. So I was leaving my second row alone. I've got negative 1 and 2. And by performing this operation, row 1 minus 2 times row 2, I have 1 minus a or 1 plus 2 gives me a 3, 1 minus my negative 2. And then I have a negative 4 minus 1 gives me negative 5. So this matrix that I end up with now has the matrix I on the left-hand side, and we claim that the matrix that we're left with on this right-hand side is A inverse. And in fact, you can verify that by comparing it with your answer in part A. Notice that these two matrices are exactly the same. So in part B, we've used this row reduction approach in order to calculate A inverse, and we see that it's consistent with what we got by applying our formula for the inverse of a 2 by 2 matrix that we were using at the beginning of this section. So let's look at some other examples, maybe moving on to more difficult cases than 2 by 2s. So in this next example, we are asked to find the inverse of the 3 by 3 matrix given here, if it exists. So we've thus far only defined the determinant of a 2 by 2 matrix, which told us whether or not our matrix was singular. So in this case, if we have a 3 by 3 matrix, how can we determine if it is singular or not? Well, there is such a thing as the determinant of a 3 by 3 matrix, which we're going to introduce in the next chapter, chapter 3. But for now, if we think back to our earlier result, this previous theorem here, we say that a square matrix is invertible if and only if that matrix A is row equivalent to the identity matrix. So we want to see if we can row reduce our matrix to the identity matrix, and in order to calculate the inverse, we would be looking at that augmented matrix A with I, and then we would row reduce A to the identity matrix in order to find our corresponding inverse. So let's take a look at this. Following the work that we had done in our previous example, let's look at the augmented matrix where we take A 1, negative 2, 1, 4, negative 7, 3, and negative 2, 6, negative 4. And let's augment that with the 3 by 3 identity matrix. So that is 1, 0, 0, 0, 1, 0, and 0, 0, 1. So on our left-hand side, we take the matrix we're given. On the right-hand side, we're taking the identity matrix of the same dimension, in this case, the 3 by 3 identity. And we now want to row reduce A to the identity matrix. So let's see what we can do here. So in my first step, well, I already have a leading entry of 1 in the first row. I want to eliminate the 4 and negative 2 that appear below it. So to eliminate the 4, I could take row 2 minus 4 times row 1. So for now, I'm going to leave my first row alone. And when I perform this operation on the left-hand side, I have negative 4 plus 4 is 0. 8 minus 7 is 1. And then minus 4 plus 3 is negative 1. In performing that same operation on the right-hand side, my second row becomes negative 4, 1, 0. Now in this same step, to eliminate the negative 2 as the lead entry in my third row, I can take row 3 and add 2 times row 1. So I would have 2 minus 2 is 0. Negative 4 plus 6 would be 2. Positive 2 minus 4 is negative 2. And then performing that same operation on the right-hand side, I would have the row 2, 0, 1. All right. So now, this matrix on my left-hand side, I have a leading entry of 1 in the first row, zeros below it, a leading entry of 1 in my second row. Now I just need to eliminate the negative 2 and positive 2 that appear above and below it to make it look more like the identity matrix. So in my next step, I could take row 1 and add 2 times row 2. So my second row I'm going to leave alone in this step, 0, 1, negative 1. And if I leave the second row alone on my right-hand side, I have negative 4, 1, 0. Then performing this operation on the first row, I might have a first row of 1, 0, let's see, negative 2 plus 1 is negative 1. And then on the right-hand side, I would have negative 8 plus 1 is negative 7, 2, and 0. And in the same step, I'm going to take row 3 and subtract 2 times row 2. So that would give me 0, negative 2 plus 2 is 0, and then 2 minus 2 gives me a 0. And then on the right-hand side, performing the same operation, let's see, I've got 8 plus 2 would be 10, negative 2, and 1. Now, notice at this stage that I have a row of all zeros for this matrix on the left-hand side. And the reason for that is, if we were looking at the second and third rows of the matrix A in the previous step, or of the reduced row matrix A, we see that those two rows are identical. So what we find is there is no way to transform the matrix A, which is on the left-hand side of our augmented matrix, into the identity matrix. I can't ever get an entry of 1 for that bottom right-hand spot with zeros elsewhere in that row. So we see here that this reduced row echelon form of the matrix A is not equivalent to the identity matrix. Therefore, it's impossible to find an inverse. This matrix A does not have an inverse. It is singular. So let's justify why an inverse doesn't exist here. So we can say here, the reduced echelon form of A is not equivalent to, or not row equivalent to, the identity matrix. So A inverse does not exist. Or another way we could say that would be that A is singular. So here we have shown that A is singular by showing that it cannot be row reduced to the identity matrix. So let's look at one last example. So in this last example, again, we have a 3x3 matrix A, and we're asked to find the inverse of this matrix if it exists. So let's take a look here. We have, give myself a little more room. We have the matrix A, which was 1, 0, -2, -3, 1, 4, and 2, -3, 4. And we're augmenting that with the 3x3 identity. 1, 0, 0, 0, 1, 0, and 0, 0, 1. So I want to try to row reduce this matrix A to the identity matrix and keep track of the same operations that I would perform on the identity matrix itself on the right-hand side of this augmented matrix. So let's take a look at it. For the matrix A, we have a 1 in our lead entry of the first row, and we need to eliminate the -3 and 2 that appear below it. So one way I could do that would be to take row 2 plus 3 times row 1. So my first row, I'm going to leave alone. And when I perform this operation on my second row, I get 3 minus 3 is 0. 0 plus 1 is 1. -6 plus 4 is -2. And then performing that same operation on the identity matrix on the right-hand side, I get 3, 1, 0. Now in this same step, I'm going to take row 3 and subtract 2 times row 1 from it. So that would give me a -2 plus 2, which is 0. 0 plus -3 is -3. And then I would have a +4 plus 4 is 8. And then I have a -2, 0, 1 when I perform that same operation on the right-hand side. All right. So now for the matrix A, we've row reduced it to where we have a 1 as our lead coefficient in the first row, zeros below it. 1 for the lead coefficient of the second row with 0 above it, but we need to eliminate the -3 as the lead coefficient in that third row. So to do that, my next step might be to take row 3 and add 3 times row 2. So my first row remains the same, 1, 0, -2, and 1, 0, 0. My second row I'm going to leave alone as 0, 1, -2, and 3, 1, 0. And my third row, when I perform this operation, becomes 0, 0, -6 plus 8 leaves me with a 2, And on the right-hand side, when we perform this, we would have 9 minus 2 is 7, 3 plus 0 is 3, and 0 plus 1 is 1. So now in my last step, well, I have a leading entry of 2 in my third row, which I see I could use to eliminate the negative 2 appearing above that in both the first and second rows. So I could take row 1 and add row 3 to it, and take row 2 and add row 3 to it. So that would make my first row 1, 0, 0. And performing the same operation on the right-hand side, adding the third row to the first, I would have 8, 3, 1. Adding the third row to my second row, I would have 0, 1, 0. And doing the same operation on the right-hand side, I would have 10, 4, 1. And the last thing that I need to do here is this leading entry of 2 that I had in my third row, I need to have as a 1 to get this to the identity matrix. So an easy way to get a 1 there would be to multiply your third row through by 1/2. So in this same step, I'm also going to take half of the third row, which would give me 0, 0, 1, along with 7 halves, 3 halves, and 1/2. So now what I have is the identity matrix I on the left-hand side, and the matrix that I'm left with on this right-hand side is a inverse. So here we find a inverse as 8, 3, 1, 10, 4, 1, 7 halves, 3 halves, 1/2. All right. So in this section, we've introduced the concept of an identity matrix, which acts like a 1 for matrix multiplication, and a multiplicative inverse. So the idea of an inverse matrix is it's some matrix that we would multiply a given matrix by in order to get back to the identity matrix. And we've seen that for 2x2 matrices, they are invertible if and only if the determinant is non-zero, and we had a formula for the inverse of a 2x2. And then towards the end of this section, we had a theorem which said any matrix is invertible if it is row equivalent to the identity matrix. And in order to find the inverse matrix, we could augment our given matrix with the identity and perform row reduction in order to convert the given matrix to the identity matrix, in which case we're able to find the inverse by performing those same operations to the identity matrix itself.